So without much further ado, I hand over to my dear Daniela. Take it away.
Thank you, Alex, and wonderful that you have us here today. And I will also keep myself very short because the most important people are coming just after me. So it's wonderful that Masa, our current Hertz Fellow, and Anthony, our current Zuconnect Fellow, will present their work today here at the cluster. The Hertz and Zuconnect Fellowships are a tool from the Zukunftskolleg together with the university to encourage early career researchers from Africa, Asia, and Latin America to join us here on campus for 3 to 4 months with a short fellowship, but also stay affiliated to us for a whole duration of 12 months. And you actually will see that Masa and Antene have already left the Zukunftskolleg a couple of weeks back and are already back home, and probably have a lot better weather that we currently have. But today's focus will be on their research. And we also have current call for both fellowships for the Zuconnect and the Hertz, and they're actually quite similar. So the fellows, when they are at the Zukunftskolleg, are just benefiting from the same. But while the Zuconnect Fellowship doesn't require any prior connection of the candidate to the university, to the 13 different departments or to the clusters, the Hertz Fellowships, they have a very strong component of early contact per se. So there's a junior or a professor of the university who give nomination proposals for those Hertz Fellows. And it's actually quite interesting that we have at the cluster this year, one of each, one Hertz and one Zuconnect Fellows. And with that, I already stop. I will put you some more links into the chat and be happy to come back to us. Current calls for the application close for Zuconnect on the 15th, and for Hertz, where all of you might still want to nominate somebody, on the 15th of March. And with that, I would like to now introduce Masa. It's very good also to see you, Masa, virtually again. Masa is a PhD candidate from Iran, and she returned, as I told you, a few weeks back. She has a very strong record at her home university. She's one of the best students there and won numerous awards as best student and as best master student. Her research focuses on graph coloring, but beside that, she's also looking into data mining, deep learning, and machine learning. So she has various different interests, but today I think she will talk more about the graph coloring. And with that, without further ado, I'll give the floor to research and to Masa.
Yeah, thank you, dear Daniela, for introducing me. Okay, thank you everyone for joining this meeting. I'd like to talk about Vertex past cover of graphs. And it's not working. The concepts I'm going to talk about are graph definition, graph covering, and graph coloring of graphs. Well, first of all, let's see what a graph is. A graph is a set of nodes, we call them vertices, which are connected together with some lines, or we call them edges. So we can have some vertices with any connection as a graph, like this graph, or we can have some connection or edges between some vertices of the graph. Well, in graph theory, we have some problems named extremal problems. In these problems, we have a parameter and we're looking for some upper bounds or some lower bounds on that parameter. So extremal problems in graph theory means how big or how small a parameter can be under some constraint. Well, graph covering and graph coloring is two of those problems I'm working on. Well, actually, my research project as a Hertz Fellow in Constant University is on covering of graphs. One of them is vertex covering, which is one type of covering of graphs. In these problems, we're looking for some minimum number of vertices that can cover each edge of the graph. It means that each edge of the graph has an end vertex in that set. As an example, you can see in the left side a graph with 7 vertices and 7 edges. We're looking for some minimum number of vertices that can cover each edge of G. If you consider 4 vertices, V1, V4, V5, and V6, you can see that each edge has an end vertex in this set. So we cover all edges with these vertices. Well, as an application of vertex covering of graphs, you can consider the edges of a graph as rows and all vertices as crossroads. Our aim is placing some security cameras at these crossroads to enable us see the whole city. And we want to use minimum number of security cameras in order to minimum all costs. So this is one of the application of vertex covering. But each problem in the graph theory, you can generalize it, and a generalization of a vertex covering is vertex k-path covering. Well, in vertex covering, we were looking for some vertices that cover each edge of G, and each edge is a path of length 1. So in vertex k-path cover, we are looking for minimum number of vertices in a graph that can cover all paths of length k-1. Similar to previous figure, we have again in the graph G with 7 vertices and 7 edges in the left side. And we're looking for minimum number of vertices that can cover each path of length 2. If you consider 3 vertices, V3, V4, and V5, you can see that we cover all paths like these red paths with 2 edges. And if you look at the induced subgraph on 4 vertices, V1, V2, V6, and V7, you can see there is no path of length 2 in these, between these vertices. So we can say that we cover the graph in the left side with just 3 vertices. Vertex k-path cover has a similar application like vertex cover. We want to suppose that we have a city and we want to equip the city with some facilities like gas stations or I don't know, security cameras or something like that. Although in these problems, we want to have one of these facilities in every L kilometers. The aim here is again using minimum number of these facilities or in order to minimum the cost. Well, till now, some researchers investigated this problem, and they have some results on cycles, trees, forests, and also they proved that for any graph G, the k-path vertex cover of the graph is between these 2 numbers. So they found a lower bound and upper bound for that. The lower bound is obtained by just counting the number of edges by considering a cover set, an arbitrary cover set. And the upper bound is by eliminating some vertices in a forest in a graph. Well, our aim is investigating the vertex k-path cover of some spatial graphs, and also we're going to find better bounds for any graph G. Well, so far we proved that for any Kennesaw graph of n and 2, when we have some restrictions on the number of on n as a parameter for Kennesaw graph, we find out that the k-path vertex cover of all of these graphs is equal to this number. It is less than the upper bound other researchers found out. And we are looking for other types of figures. Actually, when n is less than this number in the conjecture, we have some ideas that it should be again have the same value, except some cases when, for example, k is 4, we're looking for path of length 3. If we look at Kennesaw graph of 5 and 2, we can cover the graph with minimum number of vertices. I mean, minimum number of vertices in this equation. And for when k is 6 and n is 5 equal to 5, also we have the same result. But we are not just thinking on this problem. We are thinking on graph coloring because we think there's a relation between graph coloring and graph covering of graphs. And if we can find out this relation, maybe we can use graph coloring to find better bonds. Well, but what a graph coloring is? Graph coloring or a graph labeling of graphs is assigning some numbers or colors to elements of the graph. We have different types of graph coloring. Two of them, most important is vertex coloring and edge coloring. Well, in the left side, in figure above, you can see a vertex coloring of a graph. We color the vertices of the graph with 3 colors in a way that any 2 adjacent vertices, like these vertices which are connected together, have different colors. And in edge coloring, in figure below, we color the edges of the graph in which any 2 adjacent edges, means 2 edges that have a common vertex, have different colors. But we find out a relationship between star coloring and graph covering of graphs. A star coloring is a type of vertex coloring. So we are coloring the vertices of the graph such that, first of all, any 2 adjacent vertices have different colors. Second of all, there is no path of length tree in G, which is bicolor. It means that if you consider an induced subgraph on 2 color classes, like 2 color classes, green and yellow, you can see that there is no path of length tree with these 2 colors. But what is the relationship between this coloring and covering of graphs? If you eliminate vertices of 2 color classes, those color classes that have the maximum number of vertices, you can see that other vertices in the graph can be a cover set for the graph. So the vertex k-path cover is at most this one. And there are some problems I will talk about later that we are thinking of. The other coloring is defective coloring that has some connections with covering of graphs. In KD defective coloring, we are using K colors to color the vertices of the graph, but under some restrictions. And our aim is coloring the vertices of the graph in a way that any color class is an induced subgraph with maximum degree 2. So in this graph, which is a Petersen graph, we are coloring the vertices of the graph with just 2 colors. And as you can see, in each color class, like the induced subgraph on just green vertices, we have a subgraph with maximum degree 2. So we can say that this is a 2 and 2 defective coloring for Petersen graph. And the connection between this type of coloring and covering is that if, again, we eliminate all vertices of the biggest color class and add just some of them to the cover set to other vertices, we have a cover set for the graph. The problems we are thinking on, first of all, is finding some classes of graph with maximum degree delta for which the star coloring is at most delta. If we find these types of classes, actually we are able to better previous upper bounds. And the other one is finding some classes of graphs that the number of vertices in the biggest color class is is actually larger than the biggest forest in a graph that we don't know this parameter for any graph G. And the other one is finding the k-path vertex cover of bipartite graph. The last one is, I think it's a good question. As we, in previous upper bounds, they eliminate a forest in a graph. So when they eliminate a forest, they are actually eliminating or deleting lots of vertices from. They're putting lots of vertices in the set cover. But our aim is, instead of deleting vertices of a forest, deleting a bipartite graph from a forest, because in a bipartite graph we have lots of cycles, and we think that in this level we have better bonds for this vertex k-path cover. Yeah, I'm over, but I think I.
Okay, brilliant. So then I would also like to welcome Anthony. Anthony is our ZuConnect fellow and joined us here also for 4 months at the Zukunftskolleg and is back to Ethiopia now. He's a lecturer at Berhan University in Ethiopia, but has gotten his PhD from Thailand. So he moved from very